Hello and welcome to this video where today we're going to be looking at a link between an object moving in a circle and the forces acting on that object. Now for an object to move in a circle there must be a force in order to make it change direction, because if it didn't, then if we have an object here and there's no force acting on it and it was moving in this direction, it would just carry on moving in that direction. In order to make it change direction there must be a force acting on it, and this force is called the centripetal force. And it always acts in the same way. It always acts from the moving body towards the center of the circle. So our force acts in this direction here, like this. And it doesn't matter where it is on the circle. If it's over here, the force would act in this direction, and so on. If it was over here, it would act in this direction. And there are a number of examples that you can think of a centripetal force. For example, if you've got the Earth going around the Sun, where the Sun's in the middle, then gravity is the thing that provides the centripetal force. If you've got a car going around a bend, then friction provides a centripetal force. And if you've got a ball on a string and you're whirling that ball around, it's the tension in the string that is a centripetal force. Now, because of Newton's second law, we know that if there's a force, there must be an acceleration associated with it. And this acceleration, because the force acts in this direction, then the acceleration also acts in that direction. So the acceleration, again, always acts towards the middle of the circle. And this is sometimes called the centripetal acceleration. This acceleration happens because the object is constantly changing direction. If the object constantly changes direction, it means because velocity is a vector, then the velocity must also be changing. And if velocity changes, then we must because acceleration is defined as basically the rate of change of velocity, if the velocity is changing, then therefore the object is accelerating. So these 3 points are really important, because in this order it explains why an object going in a circle always accelerates. Now we can actually work this acceleration out, and it's actually fairly easier to do. It's given by this equation here. So this is the acceleration, A, and which is measured in meters per second squared, as you already know. V is the speed of the object, which is is the velocity of the object, which is given in meters per second. And omega, this thing here, not W, omega, is the angular velocity. And that's measured in radians per second. And this thing we met in the previous video. So really, if you've got something going around in a circle and you know the angular velocity, so you know how many radians it does per second, and you know the velocity, you know how many meters per second it's traveling around the circle, you can calculate the acceleration. Now, sometimes you don't know either the velocity or the angular velocity, or you only know one of them. So there are 2 other equations that are often more useful to use. So if we take the equation we've just got, so we can just see where they come from. In the previous video we saw that the linear velocity, the speed, basically the speed that this thing's going, is equal to the radius of the circle multiplied by the angular velocity. Now if we take this and we substitute this into here to get rid of v, if we just write this equation out again, we get A equals V, but we know V is equal to R omega. So that's V times another omega, so squared, gives us this. So if we want to work, if we know the angular velocity of the thing that's going around in a circle, and we know the radius of the circle, we can work out the acceleration. In a very similar way, let's put a line here so we don't get mixed up. If we start off with the same equation again, and we take this equation but write it in a different form, so instead of writing V equals, we make omega the subject, then omega is equal to V over R. Now we can use this equation to get rid of omega in this thing, so A is equal to V here times omega, but omega is V over R. So we've got V times V over R, V squared over R. So in this case, if we know the velocity that the thing is moving around the circle, the normal velocity meters per second, and we know the radius of the circle, then if we do v squared over r, it gives us the acceleration. And if we know the acceleration, we can use F equals ma, provided we know the mass, to find the centripetal force. So what I'm going to do now is basically I'm just going to do 3 examples. I'm going to do a nice simple example and then a couple ones that are a little bit more involved. So the first one is very straightforward. I want to know the centripetal acceleration of a car. The car has a mass of 900 kilograms. It's traveling around a circular bend at a speed of 10 meters per second, and the bend's got a radius of 15 meters. So I want the centripetal acceleration. So the only tricky bit now is to actually decide which acceleration equation I'm going to use. Well, because I've got the speed and I've got the radius, I'm going to use that thing there, because it's basically got the speed and the radius in it. So if I just substitute my numbers into here, v is 10, so I have 10 squared. The radius, we're told, is 15 meters, so 15. I put that on my calculator, so I've got 10 squared, 100, divided by 15, gives me 6.7 meters per second squared. So that's very straightforward. I would then want to know what the centripetal force is. Well, for that, I just go back to my GCSE physics, or Unit 2. So F equals ma. So the force is equal to the mass of the car. Well, the mass of the car is there at 900 kilograms, multiplied by the acceleration. Well, the acceleration we've just worked out is 6.7 meters per second squared. Oops. So it's 900 kilograms times 6.7 meters per second squared. And if I do that, it gives me 6,030 newtons, like that. So there's kind of like a very bog standard, very easy kind of question about a car moving in a circle. A slightly more involved kind of question is looking at a car going over a bridge. So what we've got in this case is we've got a bridge which is made up of part of a circle and a car going over the top of this bridge. And I want to know if this car comes along fast enough, then eventually what's going to happen is if it goes too fast, it's going to do what you see in films, in the movies, and it's going to actually jump. So it looks like it's jumping, it actually becomes the projectile. So it's not on the road anymore, it's now actually jumping through the air. So I want to know at what speed this will happen. So this is actually quite tricky to do unless you've actually seen it before. So what I'm going to do is I'm just going to put my forces on here. So I've got the weight downwards, which I'll write as mg, and I've got a reaction force upwards because my car's on the road. And all I'm going to do is I'm going to use F equals ma, so I'm going to use Newton's second law. And because this is moving in a circle, provided it stays on the road, if it's moving in a circle, then the resultant force must be towards the centre of the circle, because that's a centripetal force. So in problems like these, I always resolve towards the middle of the circle. So the middle of the circle is down here somewhere, so I'm going to resolve, in this case, downwards. So if I resolve downwards, my forces are mg downwards minus r, because r is acting in exactly the opposite direction. And they're the only forces that are acting on this car, because we're ignoring air resistance and all that sort of stuff. So that's the force, but it's accelerating because it's going in a circle. So it's equal to m, which is the mass, multiplied by the acceleration. So the acceleration is just given by the equations that we saw before. Now I need to pick again the right equation, but I want one with speed in it, and I've got the radius of curvature. So again, so I'm going to use this one here because it's got the speed and the radius. Now this is the kind of tricky bit, because if the car's going slow, it's just going to follow this thing here. If it goes too fast, it's going to jump off. Just as it jumps off, this R, because it's not contacting the floor anymore, is going to disappear. Because it's not contacting the force, there's no reaction force between the road and the car, so R becomes 0 as it jumps. So in other words, this thing is equal to 0 just when at the speed, just as it leaves the surface. So this thing disappears. So I can write this, I can make this much simpler. So mg minus r, but r is 0, so I can ignore it, equals mv squared over r. And I can simplify this even more because I can actually get rid of the mass if I need to. It gives me the mass in the question, so I can use it if I want to, but because I've got m on both sides, I can just cancel it out. Now I want to know the speed at which this happens, so I want to know what v is. So if I just tidy this up a little bit, put a line down there so we don't get mixed up. If I tidy this up, I get g equals v squared over r. I want to know what v is, so if I rearrange this, I get v equals the square root of g times r. G I know because it's just the acceleration due to gravity. R I know because it's just the radius of curvature. In other words, it's the radius of this circle. So I can write this out nice and simply. G is 9.81. The radius of the circle is 30. And if I just do that on my calculator, I get a velocity of 17.2 meters per second. So below 17.2 meters per second, this car will stay on the road and it'll just go in a circle. Above 17.2 meters per second, it gets all exciting and this car actually looks like it's jumping off because it's going too fast to stay on the actual road. Now the final example I'm going to do is related to, for example, a fairground ride, like a roller coaster. So in this case, what we've got is we've got a roller coaster car at the top. It starts from rest and it drops down this hill. And as it drops down this hill, it enters a circular part of this curve. Now, for those of you that have been on a roller coaster, if you remember, when you get to the bottom of a curve like this, you actually feel really heavy. And we're gonna try and work out basically the force that a passenger feels as they go through this dip, and basically this extra force, if you like. So I'm going to start off in exactly the same way I did before. So if I draw my free body diagram, my car will be down here as it goes through the bottom of the circle. I've got my weight downwards and I've got a reaction force upwards. Okay, now in this case, this is this part of the circle. So if I carried the circle on, if I can do that, then the circle will be approximately something like that. So the centre of the circle is up here. So again, I resolve towards the centre of the circle. So I'm resolving upwards this time. So I'm using F equals ma again. And I resolve upwards. So in that case, I've got R because that's upwards. Take away mg because that's in the opposite direction, is equal to the mass, again, times the acceleration. So I want to know which equation I want to use. Now, you could use any of them really, but I'm going to use this one, and that it'll become clear in a second why I'm going to use this one. So the final thing I need to do is actually try and work out exactly what it is I'm trying to actually find here. Now, as I come down here, the reason that I feel heavier is because the car is pushing back on me more. In other words, I actually feel heavier because the car is pushing back on me more, because this reaction force appears, because I'm going in a circle, to get bigger. So R is the thing that I'm trying to find. So if I rearrange this thing, I get R equals, and I'll write it like this, mg plus mv squared over R. And the reason I've written it like this is because you can see that I've now got an extra force. If I was just travelling along a flat line, so if I was just going along a flat road, I would have mg downwards, I'd have r upwards, and if I resolve this for just going along a flat road, I just have r minus mg equals 0 because I'm not accelerating. In other words, r is equal to mg. So if I'm going along a flat road, I would just get r equals mg. Because I'm going in a circle, I'm going to feel my normal weight plus an extra bit because I'm now going in this circle. So I need this. So what do I need to work out R? I need the mass. Well, I've got the mass because I'm 70 kilograms. I need G. I know what that is. That's the acceleration due to gravity. So I can work out the weight of this person. For this part, I know the mass and I know the radius because it tells me there is 50 meters. I need the velocity. Now I haven't got the velocity in the question, so I need to think about what else I've got. Now I do know how high this thing falls down from. Okay, so I can use that in order to actually work out how fast the thing is going. So I'll just get rid of this for a sec. So I know the the gravitational potential energy of this thing at the top is given by this. And I'm going to assume that all of that gravitational potential energy is converted into kinetic energy as it gets down to the bottom. And kinetic energy is given by this. So I can get rid of my m's. I know what g is. I know what h is. So I can work out what v is. So v squared equals 2gh. So equals 2 times 9.81 times 40, and that, if I do it on my calculator, is 784.8 meters squared per second squared. Now I could then work out velocity by knowing the square root of this. I'm going to leave it as v squared because I've got v squared in this equation, so it just means I can just take this number and put it straight in. So if I put all my numbers in now, I get R equals the mass. Well, the mass is 70, that's there, times 9.81. So that's my first bit, plus the mass again, so 70 times v squared. Well, v squared is what I've just worked out, divided by r, and r is the radius, which is given by 50 meters there. So I've got just a load of numbers. I basically pop them in my calculator and I end up with 1785 newtons. So this person is going to feel a kind of an effective weight of 1785 newtons. If I just work this out, then obviously this is going to be of kind of the order of somewhere in the region of approximately 700 newtons, because I've got 70 times roughly 10. So normally they would have a weight of approximately 700 newtons, but now they're actually feeling a weight of 1785 newtons. So their effective weight has gone up. So they feel a bigger force, so they actually feel like they're being squished into the car, which is why you feel heavier on a roller coaster. So in this video, what we've done is we've looked at centripetal force and centripetal acceleration, being able to describe why an object going in a circle accelerates, and we've looked at 3 examples, a nice simple one and then 2 that are slightly more involved. So I'd just like to say thank you very much for watching, and I will see you again soon.